presentation. Now I invite our next speaker, Dr. M. Suresh, Director in charge, Fluid Control Institute. His presentation title is AI helping overcome traditional challenges in process measurement and control, an engineer's and researcher's perspective. Stage is yours.
Very good morning. Yes. So that was a wonderful perspective from Vikram sir on change management aspect when we try to introduce any sort of automation or progress in the way we work and the way we live in the process industry. Welcome to you all, and this particular presentation I'm just trying to look with reference to activities or experimental tests and research activities that had been done at our end. Briefly, I'll just look at covering on these issues. I'll just briefly touch upon with reference to process measurement issue. From flow measurement aspect, we have something called impulse line blockage or clogging issues in transmitters. The second is on non-intrusive detection of fluorogens with reference to two different technologies we worked on in gas liquid two-phase flow. Third, we'll just touch upon briefly on flow measurement in large diameter pipes, specifically in the hydropower sector, that is in penstocks as well as in large diameter pipes which we see in the water industry, that is for water transmission. And again briefly I'll touch upon on the smart metering aspects with reference to water distribution as well as gas networks, and again on the to end it up with what has been happening based on the literature survey or the studies that we have carried out in oil and gas sector with reference to risk assessment or failures in the pipeline sector. Hope this 20 minutes we'll just touch upon this so that we know that this is not a new topic, that is impulse line blockage. When we have a flow measurement conventionally by differential pressure devices like orifice, venturi, nozzle, and fundamentally this blockage is something which we come to see with reference to probably depending on the fluid that is being processed. That could be crystallization or condensation, or it could be like there's a choking due to debris or whatever conditions at the impulse line entry, or sometimes maybe the failure of steam jacket or things like that could actually cause the paraffin or other kinds of products from getting choked or blocked in the impulse lines. And in many situations we also have, like in gas flow, the liquid condensate in the impulse tubes preventing an actual accurate measurement, or maybe the vice versa, that is you have gas formation or bubbles in the impulse tube which could impact your measurement. Now basically this is a scenario which is very common all around, and we had done some probably an experimental study worth about 6 to 8 months way back in 2004. So basically the impulse line study experiments were done with oil as a product flow, and we had tried to simulate the blockages by means of certain valves or by freezing the impulse tubes. Now what we had done with based on this is we used a high speed data aggression. We logged the data from the differential pressure transmitter. These are basically the outputs from a very common DP transmitters, 4 to 20 milliampere signal. You know that most of the pressure transmitters nowadays we use either piezo resistive or piezo, means whatever. We have high response sensors in between, so literally after a transfer function, the 4 to 20 milliampere signal also tries to see such good response when we set the damping factor as 0. Right? So these are just the observations what you see over here based on the transmission signal as captured by the data action with no blockage, with single line blockage, or with both dual line blockage. You know that when we have flow, the process noise is seen by both the sensor through the impulse line, and when we have one of the lines choked, what happens is you have an amplified nature of process noise being seen by the sensor, and is also seen by the sensor 4 to 20 milliampere output from the transmitter. And when both the impulse lines are choked, we know that there is a damp noise or low noise on both the limbs, and therefore it is absolutely close to silent 4 to 20 milliampere, right? Now this is not something new, and these types of research had already been done, and one transmitter, I think 3051S from Rosemont, then had a foundation field bus unit which had impulse line detection. And this particular study we had done for Honeywell for their STD1000 transmitter, and the intention was to see whether analyzing the 4 to 20 milliampere signal in a DCS can really help, because you know the process industry still uses 4 to 20 milliampere for flow measurement with your DP based devices like orifice or venturi or nozzle or whatever. So the intention was to see whether the impulse line blockages can be detected maybe in advance if possible, so that a warning or an alert can be generated in the DCS. Right? So we on our end, of course that is not connected with Honeywell, so we had just tried to assess and come out with some parametric evaluation. We found that yes, it is possible that having some correlation from the noise based on the RMS value of the signals from both the positive and the negative limb, you are able to actually determine that yes, you can say that one of the limbs is choked or both the limbs are choked, and of course for the partial blockage, the figures what you see are with maybe something like 96% choked. It is literally going undetected till about 90% is blockaged, right? So that is what we could actually see. Now this is some area that can actually be applied by means of AI, because just having a small AI learning is actually will be useful as far as the process transmitter signal is done. Now you know when you have it as a transmitter based sensing, yes, that means you need to have your entire lot of transmitters in the field replaced by units which will come with built-in detection for this, right? That may not be actually feasible most of the time. So that's the reason why DCS based situations could actually help. Now where the AI actually comes into play is, you know, the process, these transmitters, DP transmitters for flow measurement, you know, it could be there in your piping in the field with a valve in the upstream, so there is an acoustic noise traveling inside. Or it could be in a situation where it is in the vertical and you have to take care about probably two-phase flow or the frequent entrapment of air in the impulse tubes, or vice versa. Or there could be such other situations. Maybe there is a pump switched on or switched off, or maybe some such noise sources in the vicinity that can also be captured, or maybe the vibrations in the piping can also be coming as noises like this. So that is where actually you need to have a learning or a training phase when you do an installation in the field, and that actually could be done as part of your installation commissioning trials and learning trials, right? The second aspect, okay, the next I'll just move over, is on the two-phase flow. We had been fortunate enough to interact with BRC and other agencies in development of two-phase flow meters, fundamentally for gas liquid flow. Now, the particular requirement where we came in was that there was a requirement for safety studies for loss of coolant accident scenario for heat exchangers in nuclear power plants, and our requirement was that to develop a two-phase flow meter with extremely high response time so that we can actually detect the onset or initiation of bubbles formation, that is in high pressure, high temperature water. So let us assume that the water flow is at say 200 degrees centigrade or 300 degrees centigrade, and that is at a pressure like 125 bar, 130 bar pressure, and there is a sudden drop in pressure, and that will actually cause an onset of steam. Now, what happens generally in the heat exchangers is when there is an onset of steam, it can actually cause the efficiency of heat exchange to come down, and that can actually go into a vicious cycle, that this can in turn relate to poorer efficiency of heat transfer. That in turn can cause a rapid rise in temperature, and it can accelerate to a situation of breakdown of the pipes or leakages. Right? And that is actually what is unwanted for, and that was the reason why we went in for this. It took us about 3 years of development time to prepare or manufacture a custom based system, and the target was for 20 to 50 millisecond response time, and we ended up with bringing out a system for 2 to 5 millisecond response time. Of course, the type of detection that we wanted for density measurement was a gamma ray based system with cesium isotope. Only thing what we had to handle was an isotope strength of something like 1.6 to 2.1 curie, which is unheard of in the process industry, right? And for high response system, we had used an aluminum, yttrium aluminum perovskite scintillator based detector with this, so that we were able to really achieve that kind of detection response time. Now, the fundamentals with principle on which the gamma ray or X-ray based or such systems work are on Beer-Lambert's law, that the attenuation of the gamma ray is actually affected by the presence of the attenuating components inside, that is in this case the gas and liquid phases, and we could actually obtain the signature or signals from that and relate it with the pressure signal. So only the drawback is, as I said, on the radioisotope handling, and it is very difficult to get an approval if we want to really go for multi-phase meters with such high strength of radioisotopes. Especially, you know that in the petroleum industry we see the multi-phase flow meters which may have a response time like 1 minute, 2 minutes and all, and we go for a much lower source time. The nature of signals that we normally get, this is actually the intention is like we need to capture or identify the two-phase flow regime that is on the horizontal. See, let us assume there is no flow meter and you want to know what is happening inside in the two-phase flow mixture. And what you see over signal here is, you know, in a conventional multi-phase meter or two-phase meter, you have the flow entering into a process conditioner. So the process conditioner could be a homogenizer or a flow separator, and then you try to monitor the two-phase mixture flow, right? Now in this particular case we have a homogenizer which is a chamfer base. It is a very classic like the old 1960s Fremo design. So you have the mixture coming in and that's a homogenizer, and eventually downstream of that, and the gamma ray attenuation detection system is at the eventually throat, so that you know exactly what is actually with the densitometer. Now in this case the output is from the densitometer, and you can see that even by tracking or observing the signals from the densitometer with high response, what you see on the x-axis is the time axis is data captured at 1 millisecond, right? So what you see is like a 2.5 second or 2 seconds worth of time slot with reference to like horizontal bubbly flow or the wavy flow or the slug flow regime or plug flow regime that is in the horizontal, and it is actually going through the flow meter, and at the eventually you are detecting this. So You don't have to install a separate detector system on your horizontal pipe. Even from the existing meter you are able to capture this, and you could actually implement this in the AI. We had done some preliminary studies, and it is actually with BRC right now, and they are actually utilizing this for certain experimental activities. Similarly, let us assume there is no two-phase flow meter inline and you just want to do a similar assessment. Is it possible by any other non-intrusive means? So we just tried using it with simple differential pressure transmitters. Of course, we used piezo based high response units, and you could capture, and again you see what is the nature of differential pressure at a venturi for one typical flow pattern called churn flow in the vertical, right. Now in this case what you see are for a range of flow, that is gas liquid flows, even for the same kind of pattern, the nature of differential pressure time series data variation is seen there, right. So is it possible to assess and monitor what is the nature of flow with reference to the horizontal flow or the vertical flow by any of these means? That was the subject of a study, and this is an ongoing study, and there are many more other interesting things, unless the algorithms are really worked and brought in, and I will not be able to publish it right now. So I'm just shown some of the time series data, and basically some of the results from our study are that with reference to the horizontal stratified plug or slug flow as well as churn flow, slug flow there in the vertical, we could actually see the nature of flow there, and we could actually achieve about 90% prediction accuracies even by RNNs, that is recurrent neural networks like LSTM. LSTM methods have been very common in time series analysis in AI last 4-5 years, maybe since 2019 it has been in use for many such studies. And most of the studies in literature that you see about two-phase flow or multi-phase flow, you would see that support vector machines, random forest, and CNNs and RNNs, these are the types of AI or machine learning strategies that are normally found in this particular field. Now coming to flow measurement in large diameter pipes, fundamentally we as a testing agency had done for mini, micro and even large hydel projects. We had gone to sites for discharge measurement as well as for validation as well as for what is known as field efficiency testing, where the turbine efficiency is to be determined at the time of installation, at the time of commissioning, within 6 months of commissioning. So typically, for large diameter pipes, most common type of flow meters are clamp-on type flow meters, but certain cases there may be penstocks or the pipes leading to your hydro turbines may not have an access where you can install any kind of flow meters. Right. Now, in one particular case, this is on the runoff river, mini hydel power station here in Hassan. We had done an assessment where the discharge or the flow is taking place only mostly during the monsoon. Maybe 3 to 4 months you have good rains and good water, and after that it starts to go down. So the turbine or the machine is not able to produce the rated outputs. Right. So the flow, the head, all these things are varying, and you are really uncertain by looking at the measurement whether the efficiency is drastically changing or not. And that was one study we did, and it was not completed at this point of time, but this is one area where AI really is helping us because of a lot of conditions. Even we went to site with a lot of insertion type flow meters to assess whether the flow meter there is working correct or not. Of course, in this particular site there is no flow, so we just tried to gauge the efficiency by means. So basically we are looking at the electrical power output. The machine efficiency is determined as a ratio of output power by input power. Input power is determined from the discharge and the head. And IEC 41 is one standard against which we conduct all this test. Again, for large diameter pipes, one of the test methods we utilize is the dye tracer method. This has been used by us in many sites, including at the largest in the country, that is 255 megawatt turbine at Terry project. And in this, the methodology or the principle is that we need to introduce a dye. It can be a radioactive dye or non-radioactive dye. Mostly what we use is rhodamine WT, and it is basically a chemical that has luminescence when excited by a wavelength of around 558 nanometers, and you could get an emission spectra. You could use the photon counting method to determine the concentration of the dye in the water. You know that when something is introduced into flow, now depending on the flow velocity, you have a high concentration or low concentration, depending on whether flow is low or flow is high, right? So, you know, anything that is introduced, if it is stretched over a length due to the high velocity, then the concentration will actually come down. What is required at the power station is, when you introduce it, you require sufficient straight length of pipe. So it could be like more than 200D, 100D, 150D to have a sufficient thing. I have 5 minutes? Yeah. Okay. So fundamentally in this method, we need to look at a lot of aspects to ensure that the method actually is in place and works good, right? Otherwise, what happens is what you are actually measuring in terms of concentration relating to discharge is a ratio of the dye injection flow rate, and the actual concentration ratios may not actually match the actual flow that is taking place. Now, if you see at Terry or other sites, the discharge is something like 100 meter cube per second. You can just imagine that. What is the nature of flow, right? So, if a small error here is a big error there. And why is it so important in machine efficiency determination is like in 255 megawatt, let us assume that you have a 2% or 3% error in the, or deficiency in the efficiency, right? Then that's a huge economic loss for the organization. And that's why it had to be done. And when you do this method, or if you try to adapt this method for repeated use, you need to also ensure that the system is repeatable, because you don't have an expert person in flow measurement sitting there all the time. So if it has to be done by an organization, then you need to make use of a lot of learning issues at this site. So this is where AI actually would come in as an example, right? So you need to model with reference to this site. You need to take care of a lot of conditions, and the initial learning or creation actually is a time consuming approach. Another aspect is on the, you know that IoT based mechanisms are used in all the flow measurement, flow metering for water distribution as well as gas metering, because it is very easy to have most of the metering for distribution are in the rural, I should say semi-rural or urban or semi-urban areas where connectivity is no longer issue nowadays compared to the earlier times. So people have been going in for AMRs and IoT based water meters with all these kinds of protocols, so that we get to see now that we can connect more places cheaper, and you could have consumer IT systems where you can generate automatic bills and make it available to them. So most of the times utilities are looking at producing the bill accurately as well as in time, so that if you can increase the frequency of your billing cycle, you get more of an economic output from that. Now with reference to the meters performance on the tampering, or with reference to leakage aspects, that is where the economies of scale come in. And most of the times, whether it is gas distribution or water distribution, the unaccounted for or unmetered for, or what is not being metered, is where there is a huge revenue loss. And typically when companies target at bringing down like 20%, 30% unmetered flow down to say a target of 4% or 2%, that is where the economies come in. And here again, the nature of data that you get, you could apply AI. AIs could be done at the central station or at the data concentrator units that you can gather at zones, right? So that is always one mechanism that you could utilize to improve the economies of operations and management. In oil and gas pipeline operation, you have pretty lot of different types of failures with reference to pipes, the risers, the umbilicals. These are subject of study over last 2 to 3 decades, I should say. It's not a new topic, and again the target for most of the operating companies is to bring down the losses or breakdowns or the shutdowns that they see whether in subsea or others due to pipeline issues. Now it is such cases that people still rely on the use of pigging, that is pipeline inspection gauges, for looking at assessment of pipes with reference to weld integrity, with reference to pipeline damage, with reference to metal loss, with reference to corrosion. Corrosion is one of the leading issues for most of the pipe disintegrity factors. Now what happens in most of the pigging systems is that you have to look at capturing data from 6 to 10 sets of sensors, and you need to capture over the segments or sections of pipe and analyze it. And analysis is a very, very time consuming process, and that is where you need to actually shorten the cycle. And most of the types of assessment that we see in literature related to anomaly extraction, that is PCA and ICAs are used, and basically random forest or SVMs are used for classification of the problem, and in order to really assess what is the measurement or measurable aspect, we go for deep learning systems. So I'll just stop at this point. Thank you for your attention, and have a great day.
Thanks, Suresh, for your very technical presentation.